Hi everyone, I am Omar M. Flores from Davao del Norte State College, and today I'm gonna show you a simple tutorial about maximum flow of minimum cost in data structures and algorithm. So I hope you like it, and let's start. Maximum flows of minimum cost. This problem combines maximum flow, getting as much flow as possible from the source to the sink with the shortest path, reaching from the source to the sink with minimum cost. Note that in a network with cost, the residual edge also have cost. Consider an edge with a capacity, cost per unit flow, and net flow. Any flow can be decomposed into paths, some of which can be cycles. We define the cost of a path P as and express the cost of a flow as where P is the path decomposition of F. Maximum flow is just simply the maximum amount of something, anything really, that you can move from the starting node to an ending node. To read array, we're trying to find the maximum flow from a source node to sink node. We do this by finding augmenting path in the source to sink. An augmenting path is simply a path whose edges are either non-full in forward edges or non-empty in backward. Basically, a path has a capacity for flow, and you're exactly what I mean by this in this example. Here's the flow network we use. S will be your source and T our sink. We start by setting the flow to 0. The number on the left is current flow through the edge, and the number on the right is the total capacity of the flow. We're ready to start. Here's how we do this. First, find a path, then compute the bottleneck capacity with its simply the edge in the path with the smallest capacity. And finally, we augment our path. We repeat these steps until we can find an augmenting path. Let's start at S and look for a path to T. Remember, in the edges in our path must be non-full in forward or non-empty in backward. Let's, let's choose this following path first. The bottleneck capacity in A to D, the value of 8, will augment all edges with this value. Also note that each node must remain equilibrium, that is the flow into the node must equal to the flow out of them. We're done augmenting, so let's look for the next path. The bottleneck capacity is 2. In this case, because edge D to T only has the capacity of 2. Let's update the flow with this value. On the next path, I'm going to specifically choose a path with a backward edge so you can see how the algorithm works in this case. Note that our path includes going through D to A, even though the edge itself is directed from A to D. This is what I mean in by the backward edge. Also notice that data A is non-empty, so we push our units from C to D. We can take away 4 units from D to A, being the bottleneck capacity. We receive from edge A to B. Let's look for another path. In this case, edge S to A by provides their bottleneck capacity with a value of 2. We update our flow. Again, let's search a path in augmenting our flow. We have now a flow value of 19. One more time, let's search for a path. Looking at S to A, we can see the path is full. Now looking at S to C, we notice we have empty, so we cannot augment the path. Since we cannot find a path from S to T, our augment is done, and our final flow value is 19.